Okay, hi everyone. My name is Giannaros. I'm the principal investigator of the heat alarm research project, which is implemented in Greece. The basis of my presentation today is related to a novel open access human thermal bioclimate dataset that was developed in the frames of the project, which has been selected for this year's EMS Strong Award. So I'm going to provide some background information about the dataset development, and I will also present some practical applications exploiting the dataset, focusing on the communication of the relevant outcomes. So beginning, the dataset consists of hourly population-weighted values of the modified physiological level and temperature and its environmental drivers from 1991 to 2022, and for 10 different population groups in 72 fine-scale regional units in Greece. The need for creating this dataset is related to the heat alarm main goal, which is the development of a heat health warning system in Greece. Towards achieving this goal, the first major step was to assess the relationship between heat stress and health for the first time at national level, and defined location and population-specific thresholds associated with increased heat-related mortality risks. So essentially, we had to conduct a countrywide epidemiological study in order to link exposure, heat in our case, to health responses. The response data, which include mortality counts, are usually available from national statistical authorities in a standard format. However, concerning exposure, there is a lack of standardization concerning the metrics and processes used to define heat. Usually, the exposure selection is based on the availability of meteorological data, and in Greece, as well as in other countries, there is a lack of long observational time series of all environmental drivers of heat stress, including radiation, and at very high spatial and temporal resolutions in order the data to be representative of the population exposure. For example, usually data are obtained from airport weather stations, which are located far away from urban centers where most people live, and even state-of-the-art graded climate data sets which are broadly exploited in recent years in environmental epidemiological studies, are prone to misrepresentation errors in geomorphologically complex areas, as in the coastlines and islands of Greece. The third limitation in existing human biometeorological datasets is related to the physiological basis of the human thermal environment. Previous datasets, including the state-of-the-art Aero5 heat dataset, have not considered the population-wide variability in heat stress, which is connected to differences in the anthropometric data, metabolic activity, and clothing level among different population groups. To address these limitations in Greece, but also in other countries, we developed the presented dataset using the Copernicus European Regional Reanalysis. CERA was specifically selected due to the increased number of observations involved in the assimilation in the reanalysis, and because of its high spatial resolution at 5.5 kilometers, which, as shown in the map, is adequate to better represent topography, the coastlines and islands in Greece compared to the Aero5 land shown area. These characteristics provide a significant added value to CERA, especially for heat stress-related studies. This is evident in the validation of the dataset we performed in terms of replicating the observed human biometeorological conditions in Greece from 2010 to 2020. And after validation, the CERA data were combined with gridded population data in order to better represent the thermal environment experienced by the people. And the MPT computations took place for diverse populations through the Rayman Pro model. The NPT index was specifically chosen for this application because of its advancements compared to other human biometeorological indices, especially in terms of addressing the third limitation mentioned previously. In particular, the MPT thermoregulation model allows for anthropometric data, activity, and clothing modifications, which are necessary for considering the population-wide variability in heat stress. This means that given the same environmental condition, the model results in different MPT values for each population. So as mentioned in the beginning, we focus on 10 different population groups. These include male and female adults and seniors, and 3 different profiles of men and women working outdoors. The inclusion of 3 different profiles for outdoor workers reflect the variability in the work intensity needed in major outdoor occupation sectors, such as in agriculture and construction. For example, the moderate labor in the metabolic activity corresponding to modeling or labor in the second profile of workers may correspond to plastering walls or picking fruits in a farm field. It is worth noting that the dataset and the code used for its development were made publicly available as a node open access repository since version 1. And within this open science framework, the dataset has been recently expanded, and it is used for heat health studies in Cyprus, and other application activities are also taking place in the Middle East, and also in collaboration with the Goethe University in Frankfurt, using historical and future climate model simulations over the Met-Cortex domain. Focusing now on heat alarm-related activities exploiting the dataset. As I mentioned at the beginning, we first used the dataset to conduct an assessment of the heat health nexus in the country. A significant challenge we had to face during this assessment is related to the small sample sizes concerning the exposure and response data. More specifically, both types of data were divided in 72 fine-scale regional units, and then they were further divided in 6 groups based on sex, age, and outdoor occupation. So we had very limited information in our data in order to link exposure to response. To overcome this limitation, we employed a prototype hierarchical modeling framework developed by Dr. Theo Economou and colleagues using the machinery of generalized additive modeling. Among the novelties of this prototype GAN-based approach, 2 features fit perfectly for incorporating thermophysiological principles in the analysis. The first feature is that the model can consider risk variations among distinct categories, and the second is that the model can consider complex interactions among multiple exposures. So based on this model, at the first stage, we focused on the Athens urban area in the capital of Greece, and we incorporated in the analysis 2 daily exposure metrics. And the first was related to the intensity of heat stress based on the maximum NTT value, and the second was related to the exposure duration in terms of hour within a day when each population experienced strong heat stress. Traditionally, a fixed MPT threshold of 35 degrees Celsius is used to define strong heat stress, but in our case, we used the relative threshold in order to account for population and location short-term adaptation to heat. This novel analysis in the Athens urban area revealed that elevated heat-related risk is associated with prolonged exposure to strong heat stress. This is extremely important because most previous epidemiological studies focused on exposure duration in terms of days, but thermophysiologically speaking, exposure duration in terms of hours is an important determinant for adverse health outcomes. This is evident in this graph, as the high-risk areas denoted with the red are directly linked in the below graph with the more than 6 hours strong heat stress exposure within the day. Another important outcome of this analysis is the fact that the high-risk day-long strong heat stress exposure occurs under different environmental conditions in early, mid, and late warm months. This is, among other factors, this is related to the short-term acclimatization. So based on this first case study, we extended our analysis at the country level. The 72 regional units were divided in 18 wider regions based on geographical, climate, and statistical related criteria. And for each region, we developed and applied a specific GAN accounting for risk variations among the population groups and each regional unit. This was a major advancement because for the first time it was made possible to model thermophysiological heat stress and adverse health outcomes for different population groups at such a fine-scale administrative level. The graphs on the left, for example, illustrate the 10-day exposure response curves in my home region, Chalkidiki and Eastern Thessaloniki, which has not been studied before in the literature, showing notable risk variations among the examined populations and to a lesser extent between the 3 regional units. Based on these curves, we conducted a retrospective analysis concerning the increase of relative risk based on the different MPT heat stress thresholds on day 1 of exposure. These 3 plots provide the relevant outcomes for male adults in 3 different regions of Greece. For example, in Chalkidiki, this graph tells us that when MPT exceeds 32 degrees Celsius within the range of strong heat stress, then an excess mortality between 5 and 10% is expected. And as shown in the y-axis, this happens around 10 days per year. So in this plot, it is worth noting the differences in the excess mortality risk ranges in the different regions, and also the differences in the NPT thresholds corresponding to these risks. Based on this thorough analysis for each regional unit and for each population group, we concluded on these final 3 criteria for issuing a heat health warning. The first is that the 8-hour nighttime mean temperature should exceed the corresponding climatological thresholds. The second is that the maximum NPT threshold should exceed the corresponding variable threshold for strong, extreme, or most extreme heat stress. And the final criterion is that the exposure duration to one of these heat stress levels should exceed 6 hours. The font color in each of the heat stress level correspond to the different warning level. And if the exposure duration criterion is not fulfilled, then the warning is downgraded to the previous level. For the strong heat stress, this downgrade means the introduction of a yellow warning, which is also used in the case that strong heat stress is forecasted, but a lower than 1% increase in the corresponding excess mortality risk is expected. As mentioned earlier, there are differences in the same heat stress level. There are differences on the expected mortality risk among the different regions and the different populations. For example, in these warning maps, the left corresponds to female adults and the right corresponds to female workers for the 10th of July. In the Evros region in North Greece, were expected a very high warning level, but the 4 asterisks on the right indicate that a greater mortality risk was anticipated for female workers. And overall, we can note that female workers are characterized by a higher range of warning levels, higher level of warnings, because of the activity they perform, and it is considered in the computations. All this information is useful for human biometeorological forecasting and warning, but maybe a bit confusing for the general public and authorities. So communication becomes critical at this point. To avoid presenting multiple different maps, we decided to present to the public only the warning maps for male or female adults, and highlight the greater risk for specific groups in the warning text. In the warning text, we also provide some information about the drivers of heat stress and the corresponding risk in order to draw people's attention beyond just high temperatures. For example, in the map on the right, we highlight the fact that of weakening of the Odysseans in the Aegean Sea, which usually provide a thermal relief, but this was not the case on the second day of the forecast. We also provide a table presenting information about what to expect and how to protect under the different warning levels. We emphasize on reducing, for example, the activities during the hottest hours of the day. And a major gap in this communication efforts is the fact that all information is presented in Greece. So many tourists that come to the country cannot be informed about these warnings and about any weather-related warning. And unfortunately, in early June, at least 6 tourists died in the country after going for hiking on hot weather days. And these highlight the need for frequent and consistent multilingual messaging concerning the human meteorological conditions that are forecasting. And finally, some other communication activities within the heat alarm project include the direct dissemination of warnings to specific stakeholders through automated emails. They also include a video that was produced presenting information about heat stress and the heat warning, then the heat alarm warning system, in collaboration with a renowned Greek YouTube channel, in order to maximize the dissemination of the video, which is currently has more than 64,000 views. You also produce some infographics presenting information about protection measures during heat stress days. And inspired by a relevant post from the Exhaustion project, we soon we are going to compute and release publicly the excess mortality rates during the hot summer of 2004 in the country. I believe that this is a critical communication aspect for propelling people's and authorities' attention to the actual impact of heat. Beyond temperature records and heat stress level, we must empathize on how many lives have lost and how many lives could have been saved through appropriate planning, because, as we know, most heat-related deaths are preventable. Thank you very much.